Jean from NVIDIA, who's going to talk to us about scientific AI and some of the things that are going on in that domain.
Swap displays.
Yes, I'm trying to find. Thank you. Great. Yeah, actually, you said it right. One of the rare times where I'm not called Gene for an introduction.
Right.
Yeah, great to be here. Thank you for the invitation. Yeah, my name is Jean Kossaifi. I'm a senior research scientist at NVIDIA, and today I want to share a bit about the framework we kind of use to think about scientific computing, some of the challenges that have already been partially covered, and some of the future directions. So I'm going to start by maybe giving a quick intro to motivate neural operators in the framework before I dive a bit deeper. And basically, it's just the simple observation that most of modern deep learning was historically designed for discrete world of either language tokens or pixels. And so as we've heard in other talks like Martin and Ryan's talk, scientific data is typically a little different. We have, for example, different boundary conditions, different geometries, and interesting phenomena typically happen at multiple scale in natures and can be governed by partial differential equations, either known or not. And so, for example, if you look at the velocity or the temperature that you're heating from below, you may want to look at Rayleigh-Bénard convection models. Other things we look at are like computational fluid dynamics. If you're designing a car, you want to maybe minimize the drag, or you might want to do weather forecasting. Actually, yeah, weather forecasting is a particularly interesting example for us because, firstly, it's an example of a system where we don't know the exact equations governing the system. We have a constant influx of new data, so it's very hard to cheat on any benchmark. And also, it's an example problem, a great example of problem where you really want to capture those multi-scale phenomena. So here, this is just an illustration of kind of the cost, and assuming that Moore's law or whatever, the compute continues to double every year, it would still take us decades to get to a point where we can actually resolve things like storms or clouds. And so basically there is a problem that even if we continue at the current rate of improvement for compute, that's not going to be enough. And so the hope is that using AI, we can kind of further speed up things and be able to actually reason about those problems. One of the other motivations is that in many critical applications, like in weather forecasting, we don't want to just do a simple best guess or deterministic prediction, but we want to make informed decisions. And in a lot of cases, that involves reasoning about a range of possible outcomes and kind of evaluating the probability of specific events. For example, what's the probability of your hurricane making landfall in a specific region? And so this typically involves running large ensembles. So you want to run your model not once, but many thousands of times and kind of build ensembles of what's possible. And so this is kind of why we would want to use AI to kind of speed up those models. And so neural operators offer a framework to do this. So the first thing is that unlike in traditional neural networks like CNN or whatever, we don't want to work at fixed input and output resolution. So to put it differently, if you have, for example, a pin, you might be learning a mapping between finite dimensional spaces. Let's say you take as input your coordinates x, y, z, your output would be your solution at those coordinates. So you're basically learning the function for a specific instance of your PDE problem. So here what we want to do is actually learn an operator that maps between function spaces. So now you want to take as input any function, discretize on an arbitrary grid, and map it to the solution, to the corresponding solution. And so what does this mean concretely? Well, first of all, we want to be able to query at any point in the domain. Obviously, we want to decouple the resolution from the number of parameters, and that's a big problem with traditional CNN, that if you change your input resolution, you would have to retrain the model typically, and the number of parameters would grow quadratically or even exponentially with the resolution. So here we want to decouple the two. And obviously, now that we have a model that can be inferenced and trained at different resolutions, we want to make sure that it actually makes sense to query it at different resolutions. So what it means is that if you, for example, look at the flow around an airfoil, if you refine your mesh, you ideally would like to get first consistent solutions across discretizations, and you would want your operator to converge to a meaningful, useful solutions as you refine it. So basically, a lot of neural operators is simply taking traditional neural network and kind of looking at the continuum, like how does it work as you change your discretization. And lastly, as we heard in Ryan's talk, in scientific applications, a lot of time, we have very limited amount of data. And so we want something that's actually sample efficient as well. So it's kind of like our roadmap. And so how do we do this in practice? Well, this framework of neural operator mostly builds on simple tools from approximation theory. You might be familiar with the integral linear operator, which basically takes a function and projects it onto another space. So what is a neural operator in general? You typically take your input function, you encode it in some way. For example, you lift it to a higher dimensional space to facilitate learning. And then you have a series of neural operator blocks. So typically some form of a linear kernel integral transform plus some nonlinearity. And so basically all of this does is kind of takes your input functions and maps it onto a learned basis space. And we are learning this kernel K of X and Y here. And at the end, you decode your input, for example, project it back on your target space, and this is your output function. So this is a very abstract definition. So I'm going to cover 3 concrete examples of how we implement this in practice. And the first one is one you might have heard about, the Fourier neural operator, which basically says, instead of looking at this global integral transform, we're going to take a special case, which is the convolution operator. And the convolutional theorem basically tells you that instead of realizing this global convolution in the spatial domain, you can do it very efficiently in the Fourier domain. So you take a Fourier transform of your kernel, your input function, you do an element-wise multiplication in the spectral domain, and then when you inverse your Fourier transform, you get the result. And so one thing I mentioned is we want to decouple resolution and number of parameters. So it means we want to project on a fixed basis space. So what does it mean here? We're going to select a fixed number of Fourier bases. So here our bases are Fourier bases, which means it's equivalent to truncating frequencies in the Fourier domain. So typically we would truncate high frequencies. And so if you're on a regular grid, you can realize your Fourier transform very efficiently with the fast Fourier transform, which is O of n log n instead of n squared. So it's a lot more efficient. And so you can realize this very efficiently on a regular grid by simply learning the kernel directly in the Fourier domain, take your input, apply FFT, truncate coordinate, take an element-wise multiplication, and invert FFT. And so this is your spectral convolution, and your neural operator block simply adds a residual connection, which basically recovers high frequency and non-periodic information and applies a nonlinearity. And then you stack them as I showed previously, and that's your Fourier neural operator. And so that's just an illustration to show that it works well across resolution. So here we trained at 64 by 64. This is was trained on Kolmogorov flow, and this is the energy spectrum. And you can see, so it was trained on these frequencies, and the model kind of generalizes well, even on frequencies it hasn't seen. Well, if you take a neural network and just downsample the input, and then reupsample, you kind of get some aberrations on the unseen frequencies. So the second case is, what if your domain is not uniform? Well, it's actually the same principle. So if, for example, you're working on a sphere, let's say weather forecasting, instead of using Fourier basis, so sine and cosine functions on the plane, we're going to use circular functions, which are spherical harmonics. So all we do is exactly the same as before, but we replace our FFT by a spherical harmonic transform. And that's kind of the basis for the Fourier neural operator, spherical Fourier neural operator. So I won't dig too much into the detail because of the duration of the talk, but essentially, this is the foundation for the ForecastNet model, which was started originally by NVIDIA in 2022 and kind of aims at emulating global medium range weather at 25 kilometer scale. So this is trained on ERA5, which is kind of our gold standard for weather forecasting. It's all open source and it's produced by the integrated forecasting system. And so on this, we basically outperform traditional numerical weather prediction methods while being faster. And so this is back to what I was mentioning before. We don't want to reason simply about deterministic prediction. We actually want to reason about probability of events. So this was, for example, for Hurricane Harvey, I think. On the left, if you're looking simply at 50 ensemble members, you can only capture so much of your distribution. And so obviously, the more ensemble members you can get, the better you can represent the entire probability distribution. And so the more likely you are to capture these extreme winds, which are really what we want to capture to actually be able to make decisions. And so here on a single GPU, this model was 60 times faster than AFS running on a supercomputer. So the goal here, more than being better, would be to speed up things so we can actually run large ensembles and reason about the predictions. And so finally, I want to mention arbitrary geometries because we have a lot of problems where the geometry varies. For example, car design. If you want to, for example, you have a car geometry, you want to predict surface pressure or the drag. Ideally, you don't want to stick that into a wind tunnel every time. So to run the simulation, we would have as input the car geometry, which obviously will vary per car. And so we need a method that can handle first arbitrary meshes and also varying number of points. And so once again, the high level idea is again to start with this integral transform, but instead of integrating over the entire domain, if we have tens of millions of points, that would be very, very expensive. We cannot just do a local integration. So we choose a query point and we cannot do an integration over a local ball centered around that point. So we still do our linear kernel integral where we learn this kernel, but we integrate locally around the query points. And so that's useful because it allows us to query, for example, on a regular grid. So you could apply this graph neural operator, query on a regular grid, apply an FNO on this regular grid, and then decode at the end. And so that's kind of the idea behind one of our projects. So that was like kind of a very high level intro to neural operators. So since this workshop is about performance software and large scale scientific data analysis, I thought I would cover some of the challenges. And the first one is, I'm sure you're familiar with scaling laws, but essentially it's in language models, we found that if you scale compute, data set size, and number of parameters, it seems you can always improve your performance. And so far, we actually found that the same is true in scientific applications, such as weather forecasting. The problem is that, unlike for LLMs, some of the blocks are not as developed yet. And so we need specialized implementations. For example, there was no efficient spherical harmonic transform on GPU. We need to handle heterogeneous data and geometries, for example, varying geometries, which makes batching hard and can be computationally expensive. And then I/O and storage can become an issue. And so that's actually, as Hannah mentioned, data streaming infrastructure becomes needed and is not yet very efficient to use. And finally, we need to look at some different types of parallelism beyond just data parallelism. So typically people would look at FSDP, so fully sharded data parallelism, which has problems in our cases because now each device or GPU needs to keep a copy of the entire activations and input, and our inputs are typically huge. So now we want to look at domain parallelism, and it kind of makes things more complicated. So some of the ways we've solved this in practice, well, the first is custom kernels. This was an example, for example, of the spherical harmonic transforms. This is like the pure PyTorch version, which was way too slow for us to use. Triton kind of gave us a speed up, but not enough. And then some colleague, Boris Bonev and Thorsten Knuss from NVIDIA wrote some custom kernel. And that really is what allowed us to train this at scale, along with some good data and model parallelism. And so finally, since it's neural operator and you can train them at multiple resolution, you can now do most of your training on low resolution data and simply fine tune on some samples of high resolution. And the last thing I want to mention is you can factorize things. So we've looked at, because now we have tensors, because we're looking at inherently multidimensional data and weights, you can either factorize the weights or you can also factorize the gradients That's the idea behind Galore or TensorGrad, where essentially the optimizer state is what takes most of the memory. So you want to also optimize that. So essentially you can scale up the model, speed up training, and reduce the number of parameters. It's kind of a good recipe for better performance. And so just before I conclude, I want to mention that I think open source software is one of the driving force behind this current so-called AI revolution. And so I think it's very important we contribute to that. And so as you mentioned, we need to uplift the scientific software community. And so all the work we've done is actually open source. So we have research library for neural operator where we try to collect all the neural operator libraries so you can directly use them as PyTorch models. Similarly, this harmonic kernels I mentioned are also open source. So is the whole training and inference software for the ForecastNet model. And we also have some packages where we regularly port mature frameworks. So if you want to deploy anything into product or do some visualization, we have Physics Nemo and the Earth2 Studio, which allow you to do this. So this was work done in collaborations with many great collaborators. So yeah, I want to thank them all and thank you all for listening.
Do we have any questions? Everyone in this room is an expert on AI.
Are there any tutorials or documentation on how you chose to learn those specific functions? Right, you gave the high level of this integral or this space, but say I have this new domain I need to look at. Where do I start to figure out which function I'm trying to learn?
Yeah, so quick, that's kind of the structure I tried to give in the talk. I think it depends on the type of application. So like on regular grid, that would be like the FNO because it's just much more efficient. On a sphere, that would be based on spherical harmonic. Geometry would be GNO. And generally, I think it's ongoing research. We're trying to now combine this within a transformer framework. So there are a lot of architecture that try to generalize transformers to be properly resolution invariant. I think it's not quite there yet, and it's not quite clear which architecture is the best. So I think that's still ongoing research. We have some ideas depending on the type of domain, but probably a lot of it is trial and error still. I think, yeah, the field is still in its infancy, so we still need to do a lot more research. Yes.
There's one field that's not trial and error, pure mathematics.
So actually, this is very deeply rooted in mathematics. So my colleague, Nikola Kovacsky, which recently finished his PhD in Caltech, actually proved that neural operators are universal approximators so that, you know, at least we have hope of learning things. And so it's actually really grounded in theory. We also recently showed that a lot of things work well, and we showed why they work well in practice. So yeah, I agree. And I think it's a really interesting field because it allows you to kind of combine both, where you train things in practice, but you can also theoretically show that as you go to the limit, things make sense.
And I think this is related to what we were talking about. We don't have to evolve the spider brain, right? We can start with what's already been figured out with manifold theory and non-Euclidean spaces. And because the spherical harmonic, at least to a physicist, is obvious, right? If I'm solving a physical system, you know, I'm an atomic physicist by training, everything is spherical harmonics. So that's a no-brainer, right? This is how you represent functions on spheres, period, right? And it's the most compact representation you can come up with in a spherical geometry.
But that's why I'm so frustrated when the answer is you design a neural network by just like grabbing a bunch and trying them out.
Yeah,
That's like
that's very inefficient.
antithetical to the way that theorists do theory.
Right, exactly.
So I think, yeah, and that's really why these kind of workshops are really important, because there is a disconnect between the two communities. And even if you know spherical harmonics are the right tool, before we actually wrote these kernels, we tried training it. It's just, it would take forever. And then there's also this tension that you mentioned. The frustration is kind of the bitter lesson, right? We develop all this great architecture with great inductive bias. And then we find out that for some of them, you just throw a transformer at them and it kind of outperforms everything else. So it's kind of, yeah, trying to find, I think, a good middle ground. Enough inductive bias. So the spherical harmonics actually makes prediction a lot more stable as you enroll, whether for many more times, but then it's also more expensive to train.
I have a related comment, like putting on my software engineer hat. Coming from like PDE solvers, none of them are written in Python.
Yeah.
And now there's the challenge of integrating that with AI. That's all Python. And so I wanted to get kind of your impression about what the right strategies are in order to reconcile these two different software ecosystems.
Yeah, that's a great question. And it's a big pain point because, yeah, we have to kind of switch all the time between those. So we typically still use those solver, and then you save all your data, try to train your model. That's not really sustainable, especially if you want to do much more complex simulation. Let's say now we want a model instead of a simplified car design, you want to do airplane simulation in various contexts or weather forecasting. In that case, we're starting to look at streaming the data. In that case, I guess it becomes more of an engineering challenge where, as you say, you have kind of a black box, which would be maybe your numerical solver that streams data to your model. And then you need to kind of have a two-way communication where your model kind of maybe samples difficult settings, and then the simulator would feed you more of those. Or perhaps you could initialize your numerical solver with prediction from the model and kind of refine it. But I think that's almost not done at all. So
and then folks, our friends at Oak Ridge, will send you an angry email because they've noticed that you're running your job not as one big MPI process, but you start off streaming between nodes, and they're worried about the security implications. So there's like layers to this onion.
Actually, I was not too long ago at Oak Ridge talking with them. They're actually really interested in studying this kind of streaming system where you kind of have, I guess, the orchestration challenge is the interesting part for them. So I think there's a lot of opportunity for collaboration, and I think that hopefully we'll have more of this to kind of push the field forward. Because you need so many different expertises, it's impossible for a single team to really cover all the needed skills.
And just one comment about Python, C++, whatever programming language controversy. So definitely we have also seen some high performance programming systems, folks started to recognize the interoperability with Python. And for one of the examples is the MPI. A group of people are discussing MPI's fault tolerance capability. But one of the proposal is just intended for conventional C++ or Fortran, Fortran, and also seeing only these runtime stack. But now I'm telling them, we have users calling MPI from Python, or we have users calling MPI from Julia. Have you ever thought about the recovery mechanism given that programming or execution environment? Now people are now retracted their old proposal and bringing up these questions onto the table. So.
Yeah, I completely agree. I think actually that's also another big disconnect. I used to be mostly in C++ and I reluctantly moved to Python, but now I wouldn't go back. If you're doing research on, let's say, you don't really have time to code all the infrastructure, and vice versa. If you're working on the infrastructure, you don't have time to. So yeah, we kind of need to bring the two communities together. And I think it's really using Python has also made a lot of the progress possible because you can code things a lot faster in PyTorch. And even though I love doing my derivatives by hand, it's actually also a lot faster when you have autodiff. So yeah, I think making sure that the tools actually can be used by researcher and people who work on the applications, is very, very helpful. And luckily we're seeing more of this, but I think, there still could be a lot more.
Okay, so I think we should